My name is Nina Hiller, and I'm working at Siemens as a product manager. And I spent my last month here in Italy. And before we start, I want to ask a question to you. So the title of my speech is Sustainability and Energy Saving for Machine Tools. But do we really need to save energy? And what is the main reason to do so? So I will give you a few seconds to think about it. So, I mean, yes, the costs are one side. Saving energy means also fewer costs that you need to spend on the procurement of energy. But another reason is, for example, the ESPR, so the Eco-Design for Sustainable Products Regulations. So, yeah, that's a really long phrase, I know. But what is the ESPR? So it's part of a package of measures that are central to achieving the objectives of the 2020 Circular Economy Action Plan. And it entered into force this year in July. And these measures will contribute to helping the EU reach its environmental and climate goals, doubling its circularity rate of material use and achieving its energy efficiency by 2030. And the ESPR aims to significantly improve the circularity and the sustainability and also other sustainable and environmental impacts for products that are placed in the EU market. And this so-called ESPR also introduces the Digital Product Passport, the DPP. And this product passport is like an identity card of the product. So it displays relevant information of the product, as for example, technical performance, materials and where they come from, repair activities, also information about circularity, and life cycle environmental impacts. So what are life cycle environmental impacts? So that's, for example, the carbon footprint or the CO2 footprint. And what contributes to that carbon footprint? It's again the energy. The energy that was consumed during the production process of the product. And that's why we as Siemens, we publish so-called EPDs. It stands for Environmental Product Declaration. And that's a document that displays in total 16 different environmental impact categories, including the carbon footprint. So, but now let's leave the European regulations behind us. And we have a look at the Italian market. So the keyword is here, Transizione 5.0. I hope I pronounced it correctly. And over the 2-year period from 2024 to 2025, the Transizione 5.0 plan provides 6.3 billion euros in form of tax credits to companies to motivate them to both digitalize and reduce their energy consumption and so lower their environmental impacts. So it's especially made for companies that invest in innovative projects here in Italy, and they aim to reduce their energy consumption. And the innovation project must result either in a reduction of energy by 3%, referring to the production structure, or 5% referring to the production process. And the side effect is, what is better than a machine tool using less energy, working energy optimized? And to understand this topic better, that's the goal of this speech today. But first, we need to understand how the overall energy consumption of a machine looks like. So the University of Darmstadt in Germany analyzed exactly this. And they realized that only 20% of the electrical energy is consumed by the production process itself, so by the spindle. The rest, the 80%, are consumed by auxiliary units. So, for example, the hydraulic pump, the chip conveyor, some coolant units. And that means that even in production breaks, when the spindle is not running, when the machine is not producing, and the machine is turned on, that 80% of the energy consumption occurs. And this is quite a lot. And so, yeah, we need to reduce this energy consumption. But how can we do that? What can we do to reduce it? So we identified 4 key drivers or levers to do so. So the first is transparency. It's the starting point. So I talked about the 20/80 distribution in the slide before, but you need to know how it looks like for your machine or your production process. That's the starting point. Then, based on that analysis, you need to make the auxiliary units more efficient and to reduce the base load of the machine. The third one is to reduce non-productive times. So to reduce times when the machine is not working, for example, waiting on a new part or in the lunch break and so on. So this is the third lever that you can use. The last one is to optimize the machining process itself. So to optimize the 20%. So let's have a closer look on all of these key drivers now. The first one, as I told you, is transparency. So you need to analyze the energy consumption of your machine tool to find areas of improvement. Is it maybe the hydraulic pump that consumes way more energy than it should be? Does my machining process itself runs efficiently, or does it consume more than it should? These are things you should know before you implement a bunch of measures that maybe don't fit into your production. And then when you have an idea of all those points, you can start to optimize your production, to optimize your processes, and implement these measures. Yeah, a software solution to do so is part of our Sinomeric Control-E portfolio. It's called Sinomeric Control-E Advanced Analysis. And the Control-E stands for Control Energy, and it's at the same time a shortcut on the keyboard of the panel. And by pressing this shortcut, you activate the Control-E Advanced Analysis, and you can get an overview of the energy consumption of the entire machine. You can also integrate a Centron pack, an energy meter, and that makes it possible also to analyze the energy of the auxiliary units. You can see then the energy consumption directly on the HMI of the control of your panel. So now we know the energy consumption of the machine, and we realized that we need to reduce the base load. So what can we do to reduce the base load, the 80% I presented you? So one option is to switch off the auxiliary units when they are not needed or not necessary. So it's quite simple. It sounds quite simple, I know. But often it takes too much time for the operator to ramp down only specific units in a short coffee break or also in a half an hour lunch break. So to make it easier for the operator and for everybody else, you can define profiles in the control. So we call them Control-E profiles. And I will do an example. So one profile could be, okay, the machine is producing. So that means everything is turned on, everything is running, working. Another profile could be coffee break. So in the coffee break, the coolant pump, for example, will be ramped down. Another profile could be end of shift, or okay, I call it a day for now. And then all the auxiliary units in the machine will turn off. Yeah, and to show these functions, we also have a very cool demo model at our booth. So if you're interested in, you can visit the Siemens booth and we can show it to you in a live demo. Yeah, as I said before, during times when the machine is for various reasons not running productively, a lot of energy is wasted. And yeah, the auxiliary units consume still energy during that times. And so the goal here is to reduce these gaps you can see here in the diagram. So very often the machine is still used as a programming station. So that means that the part programmer stands in front of the machine, typing in the part program. After that, the program needs to be tested and run in, and this costs a lot of machining time, where the machine can't do anything else. And of course, the auxiliary units are switched on and consume energy. So the better solution would be to prepare everything before at your desk in the office, at your workplace. And this is possible with the software Run My Virtual Machine, part of the machining portfolio. And it's a comprehensive digital twin of the Sinomeric 1 CNC control. It offers the same interface and as the control itself, and it operates as the real CNC control. So you can program, test, validate, and run in the program virtually at your workplace using the digital twin, leaving the machine either switched off or machining another part. And then when everything is ready, you can go to the machine and the part program can be started. Okay, now we have created transparency, we know where our energy comes from, we've reduced the base load of the machine and prepared as much virtually as possible. So the last lever we still have is to optimize the machining process itself. So to reduce these light green bulks you can see here. So, and a software that does exactly this is called Analyze My Machining Adaptive Control. It's a feed rate control, and it optimizes the control's feed rate in real time. So either speeding up the process when cutting conditions allow so, and slowing down when geometry, material hardness, or tool conditions require it and demand caution. So this optimizes the machining process, reducing the cycle time. Less cycle time means also less impact of the auxiliary units and therefore saving energy. But that's not the only benefit. Due to the adaptation based on real-time cutting conditions, the cutting tools are protected and tool breakage can be prevented. So you have a double benefit. So I presented you with some specific examples for each of the key drivers I explained to you in the beginning, but these are not the only solutions we can offer. And in this white paper here, so you can grab your phone, you can scan the QR code and download the white paper. We collected all the software options and hardware products that have a positive impact on the energy consumption. And of course, the optimizations highly depend on your machine, on your production structure, on your environment. So there's not a one-size-fits-all solution. So you need to understand your production better and where to improve. And I encourage you to download the white paper, to speak to our expert, to find the perfect solution, especially for your needs.